Once we have defined the vector spaces, we can create some mathematical objects on them. That's the case of matrices. We define a matrix as a tuple of elements ordered according to a rectangular scheme. Here it's represented the matrix A, which has m rows. Here we have the first term, and n columns. Here we are the second term that goes from 1 to n. Every A term, for example A11, is a matrix element, and since there are n columns and m rows of this matrix, there are n times m elements. Over the matrix we can define some operations. For example, addition. We take two matrices with the same dimension, m times n, and we define the addition between these two matrices as an element-wise addition. Here we have the result of the operation element-wise as the sum of the elements. We can do this, of course, because we are talking about two matrices that have the same dimension. We can define another operation, that is scalar multiplication. We take one scalar vector, one real number, and a matrix. Then the scalar multiplication between lambda and the matrix A is the element-wise scalar multiplication. Here is the result, the generic element of the result of scalar multiplication, that is the multiplication between lambda and the element of the A matrix. As you probably already understood, we are defining the same operations that define a vector space. And that's the case because R times m times n is a vector space. As before, we have defined the two operations, addition and scalar multiplication. And the properties of this vector space that define this vector space derive from the element-wise application of the properties of real numbers. For example, we have seen before that the scalar multiplication of a matrix is the element-wise multiplication, scalar multiplication. So the property that, for example, the neutral element of a scalar multiplication derives directly from the properties of R, the real numbers, because this Aij is a real number. So now, with the definition of a matrix, we can come back and explain why images and vectors are images are vectors and tuples of numbers are vectors. Well, tuples of numbers are vectors since this is a tuple of numbers. But let's take a look to why images are vectors. Well, this is how we see an image. For example, this image has 9 pixels, 9 squares with each of them with one color. But how the computer and how we can formally define this image? Well, we can define with a 3D matrix with m in a space that is R of m times n times 3. So let's see the y, m, and n. Well, that's the width and height of the image. The number 3 corresponds to the 3 channels of an image, which is red, green, and blue, RGB. Each cell of each channel could be a number between 0 and 225, sorry, or between 0 and 1, depends on the convention that, for example, the Python library uses. But that's the point. We can interpret an image as a 3D matrix. So, since we've said that a generic matrix, we have always took 2 dimension, but it's the same for 3 dimension, a 3D matrix, the matrices generate a vector space. Also, Euclidean vector space that we demonstrated, that we proved before, that is a vector space, is a particular case of the matrices vector space, since the Euclidean vector space can be written as an R of m times n with n equals to 1. So each of these arrows, geometric vectors, can be interpreted as column vectors. Here, for example, we see that a geometric vector can be written as a matrix with m times n times 1 dimension, so it's said to be a column vector that has m components, x1 to xm. But other than addition and scalar multiplication, with matrices we can define some useful operations. That's the case, for example, of the Amadron product. In this, we introduce a multiplication type of operation that consists of a multiplication between 2 matrices. Notice that here we are defining 2 matrices, 2 generic matrices, A and B, with the same dimension, m rows and n columns. Then the Amadron product is defined as the element-wise product between the components of the 2 matrices. Pretty simple. Here we see that's the symbol for the Amadron product. We see that the dimension of the result, the matrix, is the same of the 2 other of A and B. But other than the Amadron product, we can define another multiplication that here I call multiplication between matrices in a generic way, where the 2 matrices do not have to have the same dimension, because here we have A that has m rows and k columns, and the B matrix that has k rows and n columns. As you can see in this multiplication that we see in a bit auto-computed, the k dimension is deleted, and the result is a matrix with m rows and n columns. Also, if the m and n components, dimensions are allow us to invert the multiplication, so we write B multiplied by A, the C matrix could not have the same dimension of A multiplied by B. That's the case in this picture. We have a matrix, for example, this is A, with 3 rows and 2 columns, while B has 2 rows and 3 columns. We can apply the multiplication between matrices since K is the same for the 2 matrices, which is here is 2. The result is a 3 times 3 matrix. But we can also take B multiplied by A in this case, and the result is not the same as before. But how we compute this multiplication between matrices? Well, this formula represents how we do it. But as you can see, we take two elements and we sum up in the cross dimension. Let's take a look to how to compute it in practice. And to compute it, we use the row column technique. We put the A matrix here and the B matrix here. So the result will be this dimension. That's pretty good. Now, to compute the multiplication between matrices for this element, we take the first two, we move the fingers in this way through the matrices. So we take A11, B11, and we multiply them. Then we take A12 and we multiply it by B21. Pretty nice. The last term, A13, we multiply it by B31. All these three results are summed up together to give us the C11 term. As you can see, the indices of C are 1 that came out from here. You see that A as the first index is 1 in every coefficient, and here the second index comes from the B matrix. Here we go. You see that here we are talking always about the first term, the column term. So this complicated formula can be written in this way, and is the result of the process I explained you above. Let's move on and define another particular type of matrix, which is the identity matrix. The identity matrix is a squared matrix, so the two dimensions, the number of rows and the number of columns, are the same. And the values that this identity matrix takes are 0 everywhere except for the diagonal, where the element take 1 as a value. With the identity matrix, we can introduce a new concept, the trace of a matrix. This concept will be used in further courses. So we take a matrix that, remember, needs to be squared. We multiply it with the multiplication between matrices with the identity matrix. So the result is pretty simple. The multiplication keeps unequal to 0 only the diagonal terms. If we sum all the terms in the diagonal, which is also the sum of all the elements of the matrix, we get the trace of a matrix. Here we have, as you can see, here the two indexes are the same. We define, I want you to explain you and define another two types of matrix. Let's start with the inverse matrix. So the inverse matrix can be computed only for squared matrix. So let's take a generic A matrix with the dimension n times n. The inverse matrix is defined as the matrix that, if multiplied with the A matrix, gives the identity matrix. So it's like we can see this this type of matrix, the inverse matrix, as 1 divided by A. Could be written also. For example, for real numbers, here we could have 5, a equals 5. Here is 1 divided by 5, so the result is 1. That in this case is the identity matrix. The principle is the same. Remember that since we're using the identity matrix, then the A matrix and also the inverse matrix of A needs to be squared too. The second type of matrix that I want you to talk about is the transpose matrix. Here we take a generic A matrix with m rows and n columns, and we transpose it in a way that we shift the two index of a matrix. This can be seen, this process of shift the index of the matrix. So here you see the transpose matrix elements Ej is equal to the original elements of A with index Ji. Very good. This process can be seen as the shift of the coefficients between this diagonal. So, as you can see here, the diagonal terms remain always in the same position. But this 2 is shifted, so it goes beyond the line, the red dotted line. So here we get the 5 instead goes above the line with the transpose in the transpose matrix. So here we can find the 5. Let's take a look closer to the transpose matrix by seeing that if we take the A matrix that has dimension m times n, of course we get a transpose matrix that has the dimension n times m. And considering the multiplication between matrices, we can find that we can always multiply a matrix by its transpose, and we always get a square matrix. In this case, we can multiply the transpose with the original matrix, or do the inverse, so the original matrix multiplied by the transpose matrix. The dimension of the results are completely different. You see, here we have columns. These are the columns of the original matrix. So n columns. Here we get the number of columns of the original matrix times the columns. If we follow this order instead of the multiplication between matrices, we get number of rows times number of rows. But remember that when we multiply a original matrix with the transpose matrix, no matter what's the order, we always get a squared matrix. But why introduce the matrices? Well, the matrices, as you maybe have already understood, are very useful for carrying out some single step, in a single step, an elementary operation that must be applied many times. So, for example, we want to do the addition between two elements, but this addition has to be done with hundreds, thousands of elements. We can write this operation in a simple form with matrices, which have just to bold the symbol. That's it. Also, the matrices are very useful to compute the systems of linear equations. In the slide, we see m linear equations. Here are, you see the coefficients that goes from 1 to m. With respect to n variables, here are the unknown variables that have x1 to xn. If these terms are 0, we say that the system is homogeneous. If m is a big number, it's very difficult to write these terms and to compute this to resolve these equations on paper. That's why we want to do it using a computer, but it's very complicated to code. It's very complex to code all of this equation. So let's take a look on how we can rewrite these formulas using matrices. But first, let's give a geometrical interpretation of a system of linear equation. For example, if the unknown variables are 2, x and y, and we have three equations, what does it mean to take resolve a system of linear equation? Well, in general, the solution is the point that crosses the three lines. Since we are talking about two variables, we are in a plane, and every equation defines a line. But what if we take three variables? Well, then we go in a 3D space, and if we have three equations in three variables, remember, linear equations, so x, the unknown variable, is to the power of 1 and not more. With three equations, then the solution is a 3D point, in general, of course. If we downgrade the system of linear equation in three variables to two equations, here we go, the solution in general is a line, of course, because the two planes can cross together, and we get when they cross together, we get a line. So how to solve this system of linear equations? We've already said that this is very complex to do on paper and to write it on a computer in this form. So how can we simplify? Well, first of all, we can write this coefficient as column vectors. Pretty fine. But we can do more, looking at how we defined the multiplication between matrices. Because let's take a look here. Let's change, instead of b, we just write x. And this is our b now. But the computation of a multiplication between matrices give us exactly a linear equation. So if this becomes a matrix, an A matrix, then we get, if these are the rows, m linear equations, the same as the number of rows of this matrix. So here we get a compact representation of a system of linear equation. We write all those coefficients of unknown variables in this form with a matrix, and then the x terms and the b terms as column vectors. So now, instead of this complex formulation, thanks to the matrix representation, we have just to solve this equation. Of course, under the hood, the complexity remains the same, but the representation allows us to use some of the operation that we defined for the matrices. That, for example, the transpose of a matrix and the inverse of a matrix. In fact, we want to find x here. So somehow we have to simplify this A term, which now is a matrix. And to do so, remember, in a generic scenario, we have A as an m times n matrix. We would like to take the inverse matrix, so if we multiply this by an inverse matrix, this will give a 1, and we have x equals to something. In a generic case, we need to do a trick, the trick that I've explained you earlier. We multiply both sides with the transpose matrix. So here we multiply on the right and on the left, right and left. Then, since this is a squared matrix, we can take the inverse. We multiply for both sides with the respect to the inverse. Here goes to 1, the product, so it simplifies, remains x. And here we get the inverse of this term multiplied by the transpose of a matrix times b. So the big problem here, we already seen that computing the transpose matrix is pretty simple. Take the diagonal, or with the computer just flip the index. Not a big deal. The real problem is to compute or the complexity of this formula comes from the computation of the inverse of this matrix. There are several algorithms to do so, but don't worry, we will don't look at these algorithms. Instead, I want you to explain you how to do it to solve the system of linear equations, or more. Which is the hardware that leverage this matrix representation and allow us to solve in a simple manner this type of equations. For example, to compute the inverse matrix of this thing. Well, the hardware that leverage this representation is the GPU, the graphic processing unit. The GPU is different from the CPU, and the main difference is that a CPU has few cores that are very complex and can do a lot of complex operations. A GPU has instead hundreds of cores, but these are more simple. So GPU, thanks to this enormous number of cores, can leverage those matrix multiplication on, in general, matrix operations. That's the main and fundamental difference between GPU and CPU, and why GPU is so good with matrices. For example, playing a video game on a computer involves a lot the GPU, because as we seen previously, every image is a 3D matrix, and also a game does operation on these images to compute other situations, the next frames. And to do so, not only it has to render the images, but also to compute, for example, the physics. And the physics involve points, geometric vectors. So here we are. We are always talking about matrices in some way. I'm talking here about the GPU, especially thanks to this paper. In 2019, this paper allowed machine learning to explode again, because these three authors explained how to leverage the graphic processors, the GPU, to do machine learning and to increase the speed of the machine learning training. This was fundamental, a new big bang for the machine learning field. Very, very important. Okay, so we have talked about vector spaces. We have defined particular objects on vector spaces, which are the metrics. In the next videos, we will take a look to the linear independence and bases. And in particular, we will see that bases are the skeleton of a vector space, and how we can leverage this skeleton, the basis, to a better understanding of the vector spaces, and also how to change the perspective on how we see the vector spaces.